Hello everyone. Uh, this is a second session for the course Tribology affiliated to the VTU Belagavi under the Department of Collegiate and Technical Education, Government of Karnataka. For the 7th semester mechanical students, myself Harish from Movinadagli, Department of Mechanical Engineering. Uh, from session 1, what we discussed regarding the basics of tripology and what do you mean by hydrostatic bearing, what are the how hydrostatic bearing is different than hydrodynamic bearing, how we can classify, how can we differentiate hydrodynamic bearing as well as hydrostatic bearing, and other already these are all the course outcomes. These are the 5 points which we get after completion of this course. And continuing from the session one, next is uh, expression for the load carrying capacity and flow through the thrust bearing. The figure shows the hydrostatic thrust bearing, in which you can see the larger radius is the R naught and the inner radius of the ring is called as the Ri, in which you consider hydrostatic thrust bearing, in which Q is the flow of a liquid, means flow of a lubricant across the bearing, and the W is the load acts vertically on the across the bearing as well as the journal. And these are all the assumptions what we made before deriving an expression of load carrying capacity and flow through the thrust bearing. See here, the flow is considered to be laminar because the always the flow is taken place from left end to the right end, because there is a pressure difference takes place. When the pressure difference takes place, there is a flow occurs. If the flow occurs, there should be a laminar. We have to assume. If it is turbulence, we cannot able to complete this expression. Hence, we have to consider the flow of a lubricant between the stationary surface as well as the moving surface is laminar, and pocket is deep enough for the pressure in it to be uniform. Why the pocket is deep enough is it is a highly externally pressurized load is going to act on this bearing. Hence, it is also called as externally pressurized bearing. Hence, the pocket should be deep enough for the pressure in it to be uniform. And the bearing has low frictional characteristics, and hence viscous drag can be neglected, because if it has a less frictional characteristics, there should be a the temperature generator inside the system is comparatively less, hence the viscous drag can be neglected. See, this is the equation. The flow through the two stationary parallel plates is given by this equation. Q is equals to capital B H cube divided by 12 into dP by dx. It is a pressure gradient with respect to the length of the bearing, that is dx. The B is the width of the plate, H is the thickness of the oil film, and uh, 12 is a numerical. See, in this pressure difference across the pocket, what I told you, due to the pressure difference, delta P is equals to P1 minus of P2 is equals to minus dP, because the negative sign here, which indicates as the pressure drop takes place across the bearing surface, the radius is keep on increases. Hence, the delta P is equals to minus dP. You substitute this equation in the above equation, that is Q is equals to BH cube by 12 into dP by dx, and as well as the dx is equals to dr, because we have taken the ring thickness is dr, as well as breadth of the plate is equals to 2 pi r, the circumference of the uh, bearing surface. It is in a round circle, hence the breadth is 2 pi r here, and h is equals to s naught. S naught is thickness of oil film or radial clearance between the stationary plate as well as the moving plate. After substituting all the values what we have seen in the previous slide, we will get this equation Q is equals to minus 2 pi r divided by 12 mu into dp by dr into s naught cube. You simplify this equation and you get dp is equals to minus 6 mu into q divided by pi h naught cube into dr by r. After rearranging the terms, the dp is equals to 12, 2 into 12 gets cancels each other, then we will get minus 6 on the right hand. It is in the numerator. Mu q is comes to the numerator. See, the final equation will be the dp is equals to minus 6 mu q divided by pi into s naught cube into dr by r. Integrate this equation, what we are going to get is the p, because you integrate with respect to p as well as dr by r. See, the dp becomes p and the constant term minus 6 mu q divided by pi s naught cube is remains constant, and if you integrate the dr by r, ln of r log of 10 by r plus c is a constant of integral. Hence what here it is clearly written here where c is constant of integration. You apply the boundary condition when the small r is equals to r naught, which tends to p is equals to 0. There is a pressure across the recess area is equals to 0. When r is radius of the journal is equals to r naught, then p becomes 0. Substitute this in the equation 1. What we are going to get is this equation we are going to get there is p is equals to 0, and the right side the minus 6 mu q divided by pi into s naught cube into log of r naught plus c. You take this minus 6 mu q into pi into s naught cube into log of r naught in the left hand, then the value of 6 will c will be like this only. That is c value is 6 mu q pi into s naught cube into log of r naught. Then you substitute that c value in the above equation, then what it becomes is, see here, then the p value will becomes log of r naught minus of this one the 6 mu q pi s naught q, you take it outside, then by logarithmic rule log of a by b is equals to log a minus log b. By applying that one, what we get is p is equals to 6 mu q divided by pi s naught cube into log r naught by r. That is a above expression which gives the pressure distribution across the thrust bearing when r radius of the journal which lies between the limits of r naught and ri. When you apply the second boundary condition, you see that when r is equals to ri, it tends to the pressure p is equals to pi, that is the input pressure across the bearing. You see this, what happens to the above equation. See, the q is equals to pi into s naught cube into pi, then 6 mu log r naught by ri, it goes to the denominator. This above expression which gives the flow across thrust bearing. See, this is a flow across hydrostatic bearing because it is externally pressurized bearing. Hence, from the above equation you can see the q is directly proportional to the pi. Means as q increases, the supply is also increases. See that. Now, this is called as a load carrying capacity of thrust bearing expression. Now we are going to derive a second derivation, that is load carrying capacity of hydrostatic thrust bearing. What do you mean by load carrying capacity of thrust bearing? It is the sum of forces exerted by acting at the recess area and due to the variable pressure acting across the bearing. Then what is the equation will be? You see here, the W, that is called as the load carrying capacity, is equals to sum of forces. Force is equals to what? Pressure into area. That is what I have shown here. Pi into r I square, it is the area, into pi is the equation for the force, plus the variable pressure across the bearing Ri to R0. You integrate the 2 pi r into dr. From the equation 2, the above equation becomes, see, you substitute the value of q in the above equation, then the equation will becomes, see sir, w is equals to pi r0 ri square plus pi plus integration of 2 pi r into dr. Then this equation becomes like this. You see in the next step, you take it the 12 mu q divided by h pi h naught q outside, and the log r naught pi gets cancels in the above equation, and what it remains means log r naught by r into dr. See, it is how we are going to solve. This is very easy. We have to go to the mathematics, very simple calculus, that is integration by parts. How we can solve this? Log r naught by r is a logarithmic and r is called as arithmetic. How we can solve the by logarithmic multiplication by integration by parts? That is a simple rule is there. I means integration element, L means logarithmic element, A means arithmetic, T means trigonometric, E means exponential. In this case, log r naught by r is a logarithmic element and r is arithmetic. You have to take the first function as a log r naught by r and the second function as a small r. When we integrate this equation, see here, by applying the integration by parts, what I told you now only, see, this is that integration term becomes, this becomes, when you integrate with the limits of Ri to R0, then the final equation is R0 square by Ri square divided by 4 minus log R0 by R into Ri square by 2. You substitute this value in the previous equation 3, what we are going to get is W, that is the load carrying capacity across the bearing, is pi into pi into R0 square minus Ri square divided by 2 log R0 by Ri. That is, the load carrying capacity equation is W is equals to pi pi, because you substitute the above integration what we got, that is integration by parts, you substitute in the equation 3, then what happens, the all terms will get cancels each other. At the end we got, that's a pi into pi r0 square minus ri square divided by 2 log into r0 by ri in the denominator. Then this above equation which gives the load carrying capacity across the hydrostatic thrust bearing. Thank you.